We've got 216 raised to the 2/3. And while I could square 216 and then take the cube root of it, I want to make it a little bit easier on myself. And because I've been working on my number sense, I know that 216 is actually just 6 cubed. So I've got 6 cubed raised to the 2/3. So when we raise a power to a power, we multiply exponents so that if I want to make that a fraction to make it more clear, that's 3 over 1 times 2 over 3. The 3 on top cancels with the 3 on bottom. That's just 6 squared, which is 36. Much easier than if we had squared that and then I had to take the cube root of a big number. Okay, let's try the next one. 16 to the negative 1/4. So I know the negative means it's a mover, so it's going to move across the fraction bar. So I'm going to make it 1 over 16. And then when I raise it to the 1/4 power, that means that I want to take the 4th root of it, the 4th root of 16 to the 1st power. Remember, that numerator is the power the base is raised to, but if the power is 1, you don't have to write it. Okay, so 16 I know is 2 to the 4th. So if I want to take the 4th root of 2 to the 4th, that's just 2. Looking at the next one, be careful here. We have subtraction. These are two different terms. So let's take a look at them kind of individually first and then see what we need to do. Okay, so the square root of 81, 81 to the 1/2 is just the square root of 81. So I know that that's 9 minus the square root of 81, but it's also negative. So it's going to become 1 over 81 because of the negative, and then I still need to take the square root of that. Well, the square root of a fraction is just the square root of the numerator over the square root of the denominator. So that's just 9 minus 1/9, which would be, we can either do it as a mixed numeral, 8 and 8/9. 8 and 8/9. Sorry, that's a little messy. Or we could get it as an improper fraction. I'm okay with this one if you just leave it as 8 and 8/9. Okay, so we've got 2 to the 4th over 2 to the negative 1. I see that negative exponent, and I know that means it's a mover. The 2 to the negative 1st power is going to have to move up to the numerator. So that's going to become 2 to the 5th power in the numerator, which is 32. Now, if you have homework questions, I'll be here every morning before school next week. If you want to come in for extra help, it's a bit of a weird week with Monday off and and PSAT day. You can also go to Math Lab during your study hall. We do have a review and then a major summative next week. So make sure you come in the mornings at 8:30 if you want extra help. We're going to be talking about solving log and exponential equations. For exponential equations, there are 3 primary approaches. You can either rewrite in logarithmic form and solve. You can rewrite with a common base on each side, simplify the exponents, set the exponents equal to each other, and solve. We've been doing a lot of both of those so far with the simple exponential equations. And then the third one is that if it's not possible to get a common base and the variable is on 2 different bases, take the log of both sides and use properties of logarithms to isolate the variable. So those are going to be our approaches. I just wanted to bullet them out for you so you can come back and refer to them. Let's go ahead and give them a try. For our first example, we want to solve for x. We've got 3 to the x equals 15. This is going to be one where we can just rewrite it in logarithmic form because I see my base is 3, so that would just be log base 3 of what number do we get? And what exponent do we raise it to? The order you write this is up to you. I like to think of it 3 is being raised to what power? And I know 3 is being raised to, and I know 3 is being raised to the x power, and that gets me back to the number 15. Okay, so what does x equal? X just equals log base 3 of 15. And that's your final answer. That is an answer. If we wanted to get a numerical approximation, we could go to our calculators for an approximation, but that's an exact answer. Okay, let's try another one. Okay, 27 to the x minus 2 equals 1 over 81. Okay, so I don't, on this one, I'm not going to write it in logarithmic form because I can't think of like 81 as a power of 27 just off the top of my head. So this one is one I'm going to actually rewrite them as a common base because I do know that 27 is just 3 cubed. And so that's raised to the x minus 2. And 81, that would be 3 to a negative power to move it across the fraction bar, and then that would be 3 to the 4th power, because 9 times 9 is 81, and each of those 9s is made up of 2 3s, so that would be 4 3s altogether. So that's 3 to the negative 4th. When we raise a power to a power, we multiply exponents. That becomes 3 to the 3x minus 6. Make sure you're distributing that 3 to both parts of that exponent. And then this one just stays 3 to the negative 4th. If 3 to the 3x minus 6 equals 3 to the negative 4th, what must be true? 3x minus 6 must equal negative 4. Remember, we're not doing an operation to both sides. Just by logic, we're saying if this is true, this must be true. So that once we have them set equal to each other, then it's just a quick matter of solving. 3x, if I add 6 to both sides, I get 2. Divide both sides by 3, and I get x equals 2/3. Okay, so that's 2 of our approaches. Let's take a look at another problem. Here we have 6 to the x plus 3 and 5 to the 2x plus 1. I can't just rewrite this one in logarithmic form because there's a variable on 2 different bases. And if I look at those bases, 5 is already prime and 6 is not a power of 5. So I can't rewrite them to the same base. So this is when I'm going to need to use that third approach of just taking the log of both sides. Now I could do any log base of both sides, but I want to be efficient. The fastest one to write is natural log, so that's the one we'll usually do. So I'm going to say the natural log of 6 to the x plus 3 equals the natural log of 5 to the 2x plus 1. Now, I could have left the exponents inside the parentheses. I just liked putting them outside of the parentheses to kind of set you up as a reminder of what we're going to do next. So we just took the log of both sides. So our equation is still equal. We just took the log of both sides. Now, I wrote this outside to emphasize, hey, these are just exponents. So what can we do with them by log properties? We can bring them out front. So on both sides, I'm going to grab those exponents and bring them out front. So that's going to give me x plus 3 times the natural log of 6 equals 2x plus 1 times the natural log of 5. Now notice when I brought those out front that I did put them in parentheses. That's because each part of that is going to have to distribute to our natural log. Okay, so we want to make sure that's going to look like x natural log of 6 plus 3 natural log of 6 equals, same thing on this side, both parts have to distribute to the natural log, 2x natural log of 5 plus 1 natural log of 5. And of course, if our coefficient's 1, we don't have to write it, okay? Now, we saw this technique last unit when we were solving with our variables in more than one place. We want to bring everything with an x to the left side and everything without an x to the other side. So I've got x natural log of 6 minus 2x natural log of 5 equals natural log of 5 minus 3 natural log of 6. Okay, once we have every term on this left side has an x, we can isolate the x by factoring it out. That'll leave me a natural log of 6 in the first term minus 2 natural log of 5 in the second term. That equals, on this other side, I'm going to go ahead and bring that coefficient up as an exponent. So that's going to be the natural log of 5 minus the natural log of 6 cubed. Okay. Now, to get the x by itself, we're going to just divide both sides by whatever x is multiplied by. So here we're going to divide both sides by the natural log of 6 minus 2 times the natural log of 5. When I rewrite that, I'm going to go ahead and bring that exponent back as a power on that. So that's natural log of 6 minus the natural log of 5 squared, just so you can kind of see where we're going. As you get more comfortable with these steps, you may want to do more of them in the same step, and that would be fine. So here that's going to be divided by the natural log of 6 minus the natural log of 5 squared. Sorry for the handwriting on this. The app's not letting me use my stylus to record, so I'm having to, so I'm using my fingers, so I apologize for the handwriting. Okay, so this is going to cancel on this side, and this is going to give me x equals, now let's simplify that on the other side. If we have the difference of logs, that's just the log of their quotient. So that's natural log of 5 goes in the numerator because it's positive. The 6 cubed will go in the denominator. Okay. So I'm just going to leave that as 6 cubed. And then in the denominator, we've got the difference of logs again. That's going to be the natural log of 6. And then because the natural log of 5 squared is negative, it's going to go in the denominator, and that'll be over 5 squared. Okay. Now, we want to simplify these to a single log if we can. When you have a log with the same base, this is actually the change of base formula on the right side. If we want to move it back to a single base, we can rewrite it as log with the base of what's down low in the denominator. So that's going to be 6 over 25. So log base 6 over 25, that 5 squared just becomes 25 of what we're taking the log of in the numerator. So that's 5 over 6 cubed. And 6 cubed is 216. So we'll go ahead and write that as 216. So it's log base 6 over 25 of 5 over 26 equals x. That's what x equals. All right, so that's kind of fun. We get to use those properties, manipulate it around and move it around. Okay, so make sure you're using your properties and getting practice and comfortable with that. So what if we want to solve logarithmic equations? Well, logarithmic equations have two primary approaches. We can use properties to condense it to a single log on one side before rewriting the equation in exponential form. Now, if it's already just a single log on one side, you can go straight to rewriting it in exponential form and then solving, okay? Sometimes we'll need to just condense both sides to a single log base. As long as they have the same log base, then we can set the insides equal to each other and solve for x. Now remember, we do have constraints. We talked about these last time when we were talking about the domain of logs. We do have restrictions and constraints with logarithms, okay? So that means we're going to have to check the values that we get for x and make sure that they meet those constraints. So remember, what we're on the lookout for is that the base that we're using in our logarithm needs to be positive, and the number we're taking the log of needs to be positive. So let's try some problems, remembering to check for extraneous solutions. Okay. So on this first one, we've got log base 2 of 7x minus 6 equals 3. And I'm just going to rewrite this in exponential form. That just means 2 raised to the third power equals 7x minus 6. Well, 2 cubed is 8. So now this is just a simple equation like from Algebra 1. So we've got 7x. I'm going to add 6 to both sides. That gives me 14. Divide both sides by 7, and we get x equals 2. Now, before I box that as my final answer, I want to remember to check my solutions anytime I'm solving for a log. So our base must be positive, and it is. It's a 2. And the number we're taking the log of must be positive. Well, the number we're taking the log of is 7x minus 6. So if I check 7 times 2 minus 6, and again, you can do this in your head when you're checking. 7 times 2 is 14, minus 6 is 8, which is still positive. So that will work, and so I can box it as my answer. Okay, let's try another one. On this one, we've got 2 times log base 6 of x equals log base 6 of 16. Okay, I noticed that both sides have a log, and it has a log with the same base. So I'm like, oh, cool. I'll probably use that property where I can just set what we're taking the log of equal to each other. But first, I've got to deal with this 2 out front. I need to bring that back as an exponent. So that'll give me log base 6 of x squared equals log base 6 of 16. Now, by logic, if log base 6 of x squared equals log base 6 of 16, what must be true? X squared must equal 16. Okay, so it's that same idea of log base A. If log base A of u equals log base A of v, then u must equal v. Okay. All right, so we didn't perform a mathematical operation on both sides. We just set the values that we're taking the log of equal to each other. Okay, we undo a square with square root. When we take a square root, we take a plus or minus. We pick up the plus or minus options. Square root undoes square. That gives me a plain x equals plus or minus the square root of 6. Okay, now before I box that answer, I need to check my constraints. My base needs to be positive, and it is. The base is 6 in both expressions. And then the number we're taking the log of needs to be positive. Well, the number we're taking the log of is our plain x, so we can't use the negative option, but we can use the positive option. So x is just going to be the positive square root of 6. Okay, so for this one, we've got log base 6 of x plus 3 plus 6 log base 6 of x plus 4 equals 1. Now, I'm not going to be able to drop the logs on both sides because we don't have logs on both sides and we have some terms without a log. So that's an indicator that you're not going to be able to use that technique. So let's see if we can simplify it to a single log on one side. I've got the sum of logs right now. I know that means it's the log of their product. So it's log base 6. They have to all have the same base, and they do. So it's going to stay that base. And so it's going to become x plus 3 times x plus 4 equals 1. Okay, so I simplified it down to a single log. And so now I want to rewrite it in exponential form. So 6 raised to the first power equals x plus 3 times x plus 4. Now, to save myself a little time, I'm going to go ahead and distribute that when I'm rewriting it. So x times x is x squared. 3x and 4x gives me 7x. And 3 times 4 is 12. So I'm going to go ahead and just save myself a little time foiling that out when I rewrite it. You can do that in a separate step if you want, but it's okay here. Now, 6 to the first power is just 6. This is a quadratic equation, so I need to get it equal to 0. So I'll bring that 6 to the other side. When it changes sides, it changes signs. So that'll be 12 minus 6, which will still be positive 6 here. Okay, then I need to factor it. So x squared breaks down to x and x. Factors of 6 that add to make 7. It's going to be positive here, so that'll be 6 and 1. So then my answer choices are x equals -6 and -1. Okay, I've got them in curvy set brackets because we have more than one answers. But before I box it, I've got to remember to check my solutions. So my base needs to be positive, and it is. It's 6 in both of these. And then the number we're taking the log of needs to be positive. So we've got x plus 3 and x plus 4. -6 plus 3 is negative still, so that will not work. -1 plus 3 is positive 2. -1 plus 4 is positive 3. So I still get positive numbers in what we're taking the log of when I plug in an x value of -1. So that answer works. So my answer is going to be x equals -1. You can have negative answers as long as when you plug them in, the number you're taking the log of is still positive. Let's try another one. We've got natural log . We've got natural log of x plus 1 minus natural log of x. I've got the difference of logs, so I want to simplify that down to the log of their quotient to make it a single log. The positive term goes in the numerator. The negative term goes in the denominator. So that's natural log of x plus 1 over x equals 2. Now, I don't have a log on the other side, so I'm going to have to rewrite this in exponential form. So I'm going to raise e to the second power, because when it's natural log, my base is e, equals, or gets me back to x plus 1 over x. Okay, let's start solving this now. Break out those algebra skills. We're going to multiply both sides by x to get rid of the denominator. That'll cancel. That gives me, now e is a number, so I'm going to put it out front as the coefficient. So e squared x equals x plus 1. I want every term with an x on one side and every term without an x on the other. So that's going to be e squared x minus x equals 1. Why did I want every term with an x on one side? So that I can factor that x out. That leaves me e squared in the first term minus 1 equals 1. Now I'm going to divide both sides by whatever x is multiplied by. So I'm going to divide both sides by e squared minus 1. That cancels and gives me x equals 1 over e squared minus 1. big fraction bar there. Okay, now E is a positive number, 2.17159 approximately. When I square it, it's going to be even bigger and positive, and if I subtract 1 from it, it'll still be positive. So that's a positive x value, but I still need to check it. If I plug it in to x, it is a positive number, so it'll be positive. If I do a positive number plus 1, it's still positive. So in both places, it will work. And so that is going to be my answer, x equals 1 over e squared minus 1. Okay. Last example. We've got natural log of x squared minus 4 natural log of x minus 12. Now, this is going to use a technique called U substitution, and you don't have to use U substitution if your algebra eyes are strong and you can see this for yourself already. But a lot of you may not realize what's going on here, and so you might want to use this technique called U substitution to help you see it. Okay, when I look at this problem, I see I've got natural log x squared, I've got a plain natural log x, so natural log x squared, a plain natural log x, and a constant. That may not mean anything to you. If you're, first time looking at this, you may not see it. But to me, what I see, if I let u, and that u is just a variable, it's called u substitution because u is not a variable we use often, so we use it for this and call it u substitution. If we let u equal natural log of x, so if we let u equal natural log of x, this becomes u squared minus 4u minus 12. And U substitution equals 0. U substitution is just a technique to help us see with our algebra eyes what we need to do with this equation. When I write it in the U substitution form, u squared minus 4u minus 12, I'm like, oh, that's just a quadratic. I need to factor it and finish solving. U squared breaks down to u and u. If it's going to multiply to make negative 12, one has to be positive and one has to be negative. When the signs are different, I want factors of 12 with a difference of 4. So that'll be 6 and 2. Because I want the middle term to be negative, I'll make the bigger number negative. So that'll be 6 and 2. And there are my factors. Okay, now that we know what we need to do, we can come back and do that. So we can factor not using the u, but using what u stands for, which is natural log of x. So that's going to look like the natural log of x plus 2 times the natural log of x minus 6. Okay, now some of you could have gone straight to that. You could have seen we just have a squared term minus 4 times that term minus a constant. And you could have gone straight to these factors. So if your algebra eyes are strong and you can see that, you can go straight to these. You don't have to use the U substitution technique, but it's a technique that lets us see, is there something that I can do with this that I'm not spotting? Okay, so once we have our two factors, we know if this times this equals 0, then one of those two factors must equal 0. So either natural log of x plus 2 equals 0 or natural log of x minus 6 equals 0. So we're just taking the two factors and setting them equal to 0. So I'm going to subtract 2 from both sides, so that gives me the natural log of x equals negative 2. Then I'm going to rewrite that in exponential form. I know if it's natural log, my base is e, so e to the negative second power equals x, which means x equals 1 over e squared. Okay, let's do the same thing on the other side. I'm going to add 6 to both sides. That gives me natural log of x equals 6. Then I'm going to rewrite it in exponential form. So I know my base there is e to the 6th power. My base is e because it's a natural log. So e to the 6th equals x, and so I'll just leave that as that. Now, e is a positive number, so when we raise it to a power, it's still going to stay positive, so these are positive numbers. When I plug it in here, then what I'm taking the log of is positive, so that's good. When I plug it in here, what I'm taking the log of is positive, so that's still good. So it meets the requirements for the constraints we have, so both of those can be answers. I usually prefer that you go ahead and rewrite it in set brackets. If we have a set of answers, the smaller one is 1 over e squared, so it goes first, and then the larger one, e to the 6th. Both work, so both get boxed as our final answers. Okay, that's it for our examples in our notes today. Good luck. Like I said, you can ask questions when I'm back, or go to study hall, or come see me in the mornings at 8:30 before school.